Hey, and we're back again, talking about a little bit more about activation energy. So, what we talked about last time was how kinetic energy is changed into potential energy, and it is done. Enough kinetic energy is changed into potential energy in order for some reactants to turn into an activated complex. So, as we see here, potential energy starts to go up because kinetic energy is changed into potential energy, and what we get is it reaches a certain point where the reactants turn into what is called an activated complex. And this is a very, very unstable, not really a product. It's a in between a reactant and a product. It's very, very unstable, and it's the step right before it reaches products. So it's very, very short-lived. It only stays there for a tenth of a second, and then it quickly turns into products. So again, kinetic energy is turned into potential energy, and then it reaches an activated complex, then becomes products. So reactants require a little bit of energy, and this little bit of energy that they require is called activation energy. And here we can see the energy that it does require is this amount. So we'll write this in blue. So right here, this amount right here is what is called the activation energy. And the symbol for activation energy is E subscript A. Okay, so the activation from reactants products is EA in this case. Now, how is kinetic energy related to this graph right here? How is kinetic energy related to activation energy? That's what we want to look at today. So moving on, we see here something very, very similar. We see this time an endothermic reaction. So again, we have our activation energy, which is little a right here. So we can write here the activation energy. Now, C is the difference between reactants and products. And C, therefore, the difference between reactants and products is also called the change in enthalpy, or in other words, delta H. So up here is our products. Okay, and up here again is our activated complex. Okay, so here's an endothermic reaction. We have a much, much larger activation energy, and in order to reach our product. So it has a lot more kinetic energy needs to be changed into potential energy in order to become products. Now, how does this relate to kinetic energy? Well, let's take a quick look. So here's our kinetic energy distribution graph. If we remember, an increase in temperature means that, so at T2, right here, temperature 2 is an increase in temperature, and we have more molecules that have enough energy to react. Now, how does this green area relate to our activation energy? So if we turn our distribution graph on the side, so it's the exact same graph, we just rotated it 90 degrees, we can see that this, which is what we call our minimum energy, this is the minimum energy for a reaction to happen. So sometimes we just call it our ME, our minimum energy for a reaction to happen. So for a reaction to occur. And that's what this line represents right here. Okay, so this is the minimum energy for a reaction to happen, and what we see here, this number right here, potential energy, this is the amount of energy that we need for it to reach the top of the activation energy. This is the amount, and we can line this up to be just right there. And so what we can see here, if a particle has this much kinetic energy, now that much kinetic energy can be changed into this much potential energy, which is not enough energy for that particular particle to become a product, or for it to undergo a reaction. Okay, so the minimum energy a particle has to have this amount of energy right here. So that's why at a higher temperature we see more particles having enough energy to go over this bump. Enough particles have these particles here have enough energy to go over and meet the activation energy requirements in order for reactants to become products. Okay, and this is how the distribution graph relates to this potential energy and activation energy kind of graph right here. Okay, because normally on this graph right here, you cannot see any type of temperature, or you can't see any type of kinetic energy. But how these two relate is this way, this line right here. So again, these particles right in this area here, all these green particles, these have enough energy. This can become, these particles have enough energy to react. Now, that does not necessarily mean they will react. Okay, they do have enough energy to react, but they still need to collide. They still need to hit each other. If they don't hit each other, there won't be a reaction. And they also have to hit each other the correct way. So a particle has to hit another particle in a very, very specific way. They have to hit each other. If a particle hits another particle by just grazing it, so it hits it and then kind of bounces off this way, they kind of don't hit each other with a maximum amount of force, well, a reaction probably won't happen. So there's a few things they need to have. They need to have enough energy, they need to hit, and they need to hit each other correctly for a reaction to successfully occur. Okay, and we'll talk a little bit more about that later. Okay, next time.